I think technically American baseball is like American cricket. We're talking about what came first.
Cricket's ancient.
That's what I mean. That's what I was saying. Yeah.
Baseball is actually an adaptation of a girls' game, an English girls' game called Rounders.
Really? Interesting.
No, is anything wrong with that?
Yeah, we won't let women play baseball. Go figure. Periodic trends today? No?
Still doing electronic orbitals. All right. So we have settled on the fact that there's more than one kind of environment for an electron. They can be in s electrons, p electrons, d electrons, or f electronic orbitals. Did I show you the picture for the f electronic orbitals? No. I pulled it up and then I didn't show it. I'll put the screen on. And they are different shapes, different sizes, and you can predict that the electron resides in one of these orbitals by just looking at the periodic table. Again, the periodic table turns out to be this just massive font of information for us. It's not something that you should be shying away from. It's a hint sheet. Okay. And then we figured out that the s block only contained one orbital. So the number of electrons that can go into an s orbital is either 0, 1, or 2. And that there were 3 p orbitals, and the p block is 6 atoms wide. So each of the p orbitals can hold a maximum of 2 electrons. Okay. And the shapes of the orbitals are on the screen. S's are spherical, P's are that, you know, like I said, it's a dumbbell, so figure 8. And then D's are clover leaves, and then F's, that's why we're not going to draw F's. F's have more nodes. As you go down, you have 0 nodes at the top, 1 node for the P, 2 nodes for the D, and then 3 nodes for the F. And it makes things like entertaining to have to draw those. We won't be doing the F's. Plus the chances of you ever encountering anything that contains F orbitals is limited. Okay.
Are those the ones that are in?
It's the block at the bottom.
Yeah.
From cerium to lawrencium. Okay. So let's count them. Let's count them in. And what we're going to do is look at an orbital's occupancy. How many electrons does it hold? And it's governed by 3 rules. This is a thing that we're going to ultimately end up calling electron configuration. Configuration in chemistry is just an accounting, a tallying up of what have you got. So in some branches of chemistry, configuration is you're going to look at the structure of the chemical and say, this carbon is attached to that hydrogen and that chlorine and this oxygen. It's just a counting up of what have you got. Electron configuration is we're just going to count the electrons and tell you where they are. That's it. And it's governed by 3 rules. Those rules are Aufbau. Anybody speak German? No German speakers? Well, I'll tell you, I could just make up what it means then. Aufbau means building out. It means that you start closest to the nucleus and you build outwards from there. The smallest electronic orbital occurs in period number 1. Remember, n equals 1, n, principal quantum number, determined what size was. So the atoms in period 1 have the smallest electronic orbitals, and then period 2s have larger, and then period 3s have larger, and period 4s have larger. We build outwards. This is the building out principle. We've used the word principle twice in this chapter, spelled 2 different ways. N was the principal quantum number. Aufbau is the building out principle. Principal was like, that's your number 1. Principle is a concept. This is a building out principle, which means you need to fill the orbitals closest to the nucleus before moving on to put electrons in orbitals that are further out. Okay. Our orbitals are named S, P, and D. And they are named also by the period that they are in. So when I look at the periodic table, period 1 only has an S. Period 2 has S and P. Period 3 gets S's and P's and D's. Don't stare too hard at the periodic table, because what I've written on the board isn't actually displayed on the periodic table. This is something that is a surprise, that the math dictates something, but what actually happens doesn't happen in the order that we were expecting. Okay? So that's just what the S and the P and the D means. As you go further down the periodic table, you get more and more types of orbitals, but at the top, we've only got the S. So our sequence of orbitals is you fill the 1s before you fill the 2s, before you fill the 2p, before you fill the 3s. If we look at period 3 on the periodic table, it says sodium and magnesium. And that's 11 and 12. And aluminum is 13. So that's 3p. And then we get to 4s. And what happens next is the math, when we have n equals 3, tells us that L equals 2, which means a d orbital. So there's supposed to be a d orbital here. There's supposed to be a 3d orbital. But it hasn't shown up. It didn't show up at position number 19. It showed up at position number 21, that the 4s leapfrogs it. So we're going to fill the 4s before we fill the 3D, before we fill the 4P. This one is out of sequence. It is easy to look at this sequence and say that the 3D is out of sequence. It's the 4S. And the 4S is out of sequence because the S is a sphere. And the sphere is nature's perfect way, most efficient way of packing volume against surface area. It gives you the most volume using the least amount of surface area. Yeah.
So this might be a little out there, but is that one of the reasons why all planets are spherical?
Almost certainly. Except this one, because this one's flat. When the university tells me that I have to give equal time to, well, electron orbitals might be flat. So you can't just tell them that they're spherical because they might, no, yes. Nature's way of, anybody know what the mathematical thing for a sphere is? V equals 4/3 pi r cubed. Don't mind, don't erase that. Strike it from the record. It's just the most efficient way of putting volume without using surface area. So the electrons here in the 4s, which is supposed to be here, do a better job of surrounding the nucleus. They do a better job of surrounding the nucleus. All right. And the Ds, they have to approximate a sphere. The S is a sphere. All right. The other rule that we have, we've got 3 of these, is called Pauli's exclusion principle. Pauli's one of those guys that was around in the 1920s, 1910s, when all of this was kicking off. Einstein, Niels Bohr, Max Planck, Schrödinger, Heisenberg, Paul Dirac. Dirac does not get the love from history that he deserves. Dirac's really the guy that does all of the electron work. This guy figures out that no 2 electrons can have all 4 quantum numbers be the same. And that if you put 2 electrons in the same orbital, then 3 of those quantum numbers will be the same. But it's that last one, the spin, that will be different numbers. Because a moving electron, a moving charge generates a magnetic field. I've got a north and a south pole to this magnetic field. And if I'm putting 2 magnetic fields in the same box, they better not be pointing in the same direction. You try and put 2 magnets together with north and north, and they will flip. Okay. So electrons in the same orbital will be spin opposed, one up, one down, north and north. Okay. Which are, that's as far as we need to go. Again, electrons. If you decide to read a little bit more, you find out really, really bizarre behavior. That if you start with 2 electrons in an orbital and you separate them, and then you send one off somewhere, and then you do something to this one, now that they're not in the same orbital anymore, to make it spin change. This one, which might now be millions of miles away, flips. It's called a quantum entanglement. And all of those people looking for time travel and interdimensional travel or whatever, I'd think, well, that doesn't make any sense at all. It makes no sense. There's something additional going on that we don't know yet. There's still plenty that we don't know. We've cracked, hey, here's an atom. We're good with that. I can tell you what's going on inside, and at the surface level, I can tell you what all the little moving parts do. But I can't tell you how it works or why it exists. All of that stuff is still. And the harder you look, the more mysterious it gets. So I'm going to just give you this at the small level. The electrons in the same orbital must be spin opposed. One spin up, one spin down. We call them up and down. We call one of the electrons spin up, and we call the other one spin down. The third rule has a clause to it. It starts with an if. And this is Hund's rule. If electrons are placed in degenerate orbitals, okay, so we started this with an if, and then we used a word that none of us know the meaning for, okay. Degenerate in physics means having the same energy. So there is no reason for us at this time to believe that the px, the py, and the pz should be different from each other. Those three are degenerate. They have the same energy. When they're unoccupied, they have the same energy. Okay, so I'm going to give you an example. The py, don't know why I didn't start with x, and the pz, I'm going to go back and fix that. So that it says px, py, and pz, because that's normal. They're the same as each other. They're just pointing different directions, right? We have not introduced anything that would tell us that those are different. So if you place electrons into electrons that belong to a group, it's another way of thinking about what degenerate means. They belong to a group. They can be grouped together. If then if you place them into empty orbitals before pairing them up, that's gonna be the lowest energy. Electrons repel each other. I'm about done with that pen. Electrons repel each other. If I'm a carbon, I'm in position 6 on the periodic table. That's the second atom in the 2p block. So I've got 3 orbitals that I'm going to put 2 electrons into. if I put them both into the px, then they repel each other. The x and the y and the z are at 90 degrees to each other. So if I put one into the x and one into the y, then they don't repel each other. Lower energy. Okay. All right. Are we good? It's coming off the board. Going to draw something that are called orbital energy diagrams. And I'm going to put the atom here, its label, and then I'm going to treat each electronic orbital just like a box. It's just a box. Aufbau tells us the electrons go into the 1s orbital before they go into the 2s orbital, before they go into the 2p. Okay. Here's hydrogen. Hydrogen has 1 proton, no neutrons, 1 electron. There it is. Electrons are symbolized by an arrow. It's an arrow, but it doesn't have 2 barbs to its arrowhead. It only has 1 barb to the arrowhead. Okay, that's our symbol for an electron. If we ever want to tell you that it is moving from one place to another, we curve that arrow and we say that the electron was here and now it has moved to be over there. And if we ever want to tell you, well, guess what this means? What would that arrow mean? If this is the movement of 1 electron, what would that be?
2.
That's the movement of 2 electrons, which turns out to be the basis of all acids and base chemistry, which is the basis of all chemistry. That we have a base and we have an acid, and the base recognizes the acid and the base kills the acid. That's really the basis of like 80% of our chemistry. More than that, more than 80%.
Like kills, you mean neutralizes? Okay.
Okay, I've got 1 electron. It's in the 1s. Okay. Here's helium. You're going to be drawing on lots and lots and lots of boxes. See if you can figure out what helium would be. You have 3 rules. Helium is position 2 on the periodic table, which means it has 2 protons, which means it has 2 electrons. I need to fit 2 electrons somewhere in these boxes. Aufbau says, don't you go start using these until this one is full. So I have to fill that one. So I put 2 electrons in the box. Right? No, not right. What have I done wrong?
They're both facing the same.
They're both pointing in the same direction. Which breaks whose rule?
Pauli's.
That's Pauli's exclusion principle. Do not put two electrons in the same box pointing. I'm going to draw these bigger. I'm going to erase these and draw them bigger. It's clear that if you do that to me, that means I'm going to make these bigger. That needs to be pointing this way. Okay. It's going away and coming back. Hydrogen's simple. It's just one electron. Helium has to obey two rules. Hydrogen only obeyed one. It only has to obey Aufbau. It's only got one electron. It starts at the beginning. When we get to helium, I have to obey two rules. I have to start at the beginning, fill this orbital before I'm allowed to move out to that orbital, and I have to obey Pauli's exclusion principle, because spins have to oppose each other, and one is spin up and one is spin down. Okay? Do you think we could skip over lithium and go straight to beryllium? Or should we do lithium? Let's do lithium then. There's lithium. Aufbau says, start at the beginning and work your way out. Lithium is in position 3 on the periodic table. Its atomic number is 3, which is the number of protons. Protons are positive, which means it needs 3 negative things to counterbalance those positive charges, which means it has 3 electrons, and they go 1, 2, 3. Okay? These boxes are changing shape. That's carbon. Go do carbon. Carbon is in position 6. It has 6 protons, 6 neutrons, 6 electrons. You have to obey Aufbau. Start at the beginning, close to the nucleus, in the smallest orbital first. Build out from there. You have to obey Pauli's exclusion principle. The 2 arrows in a box have to be pointing in opposite directions. And now, for the first time, we're in the P block. The P block contains a 2px, a 2py, and a 2pz, and we have no reason to believe that they are different from each other and that one would be favored in favor of the other. They are degenerate, which means we have to obey Hund's rule as well. Okay. Six. 1, 2, 3, 4, 5. Where does the next one go?
Right.
6. Aufbau, start at the beginning. Pauli's exclusion principle, pair them up, one down. Hund's rule, if these orbitals are grouped together, put them into empty boxes. Put them into empty boxes.
But
Put them into the empty boxes before pairing them up. If you stick around for a bit more chemistry, when we get to inorganic chemistry, we actually quantify Pauli's exclusion principle. Not with a real number, but we express it as being bigger or smaller than another quantity that shows up. That it's in contest with the splitting energy. And is P bigger than delta?
in this scenario, does delta still signify change?
Yeah, it's the gap between orbital energy. Don't worry about it. We're 2 full years away from that yet. Okay, you should be able to do nitrogen, and you should be able to figure out oxygen. Have a stab at it. We seem to finish first. I'm either mortally wounded when I put the red ink on. No, it's just ink. What does the orbital energy diagram for nitrogen reveal? Up, down, up, down, up, up, up. Yeah. Okay. This turns out to be a little bit special. This is, there's something going on here. This is X and Y and Z. And that's my PX. And I put an electron in there somewhere. It's somewhere in those balloons. And then here's my Y, and there's an electron in there somewhere. And then here's the Z, and there's an electron in there. And they can never be at the nucleus. It means that this electron is 90 degrees away from that electron, which is 90 degrees away from that electron, which means they basically don't ever get in each other's way. This is a half-filled orbital. And a half-filled orbital is stable because its repulsion is low. There's only one thing better than a half-filled orbital. Guess what that is?
Filled orbital?
Yeah, it's a filled orbital. If you jam every single place full of electrons, you find yourself at the end of the period in group 8. And we know from behavior that the elements in group 8 are inert. They don't react with other stuff. That the heliums and neons and argons and kryptons of the world exist as atoms. They don't even interact with other stuff to make molecules. Kind of a lie, but it's mostly true. Okay? So the only thing more stable than that is a half-filled, is a filled orbital, which we would write if you could squeeze it in, we would squeeze it in all the way down here for neon. Okay. But we have a decision to make for oxygen. Oxygen has a total of 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. I pair them up when I have to. And when I pair them, one goes up, one goes down. Okay? So I get Aufbau, Pauli's exclusion principle, Aufbau, Pauli's exclusion principle, Hundrel, Pauli's exclusion principle. Neon goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a filled orbital. Filled orbitals are stable. They are complete. They have served their purpose. Half-filled are stable because they have less repulsion than semi-filled. Okay, so if I said to you, go ahead, find rhodium on the periodic table. It's position 45. It's right in the middle. It's right at the center of gravity of that table. And show me its electron configuration. How many boxes and arrows are we going to draw? It's quite a lot, right? All right, let's invent a shorthand for this. The shorthand for this is 1s1. That's the period. That's the block. And then that's the number of electrons. That's a big 1, a lowercase s, and a superscripted 1. What's helium going to be? One S2. What's lithium going to be?
3.
Look at
2s3.
1s2, 2s2.
I have 2 electrons in the 1s. That's my 1s2. And then I move on and I put 1 electron in the s orbital in the second period. So it goes 1s2, 2s1. What would carbon be? 2p2. I have 2 electrons in the 1s orbital, 1s2. I have 2 electrons in the 2s orbital, 2s2. And I have 2 electrons in the combined bunch of degenerate orbitals that belong to the 2p, 2p2, which makes nitrogen one s2, 2s2, 2p3, and makes oxygen 1s2, 2s2, 2p4, and makes neon.
That's two S2, 2P6.
There you go. Good. Good. All right. Sometimes you want to draw the diagram. Sometimes you want to draw the diagram to show the person, I've got 3 separate electrons here, which you don't get by saying 2p3. You don't immediately get that. Okay? So sometimes we want to draw these diagrams. Sometimes we want to prove a point. Other times, almost all other times, we're just going to use this. This is now our electron configuration. When you see somebody say, show me the electron configuration, this is what they mean. All right, let's poke around on the periodic table, see what we can see. Right. Let's do some big ones. We have a few minutes. Let's look at the periodic table, put it out a bit, and see what we can figure out. What's the electron configuration for sodium? The days when we have in-class exams, you have periodic tables for everybody else. Now you can put your finger on it. And what you do is you put your finger on it and you just read. Top left to bottom right. You just read a line across and then another line across and you go, I'm going to count until I find sodium. And it reads 1s2, 2s2, 2p6, 3s1. Right. Do that for calcium. Keep your finger on the page and convince yourself that you're doing it right. Those of you who've seen this before know that there is another shortcut where you write what is called the closed shell. Calcium comes after argon. So some people cheat, and instead of writing all the configuration up to argon, they just write argon in square brackets. I'm not going to allow you to do that. I want the whole thing. This is a training exercise, right? After this, you can do it. You can do it in chemistry too, but not in chemistry 1. What's the answer?
Calcium. 1s2, 2s, 2s2, 2p6, 3s2, 3p6, 4s2.
Silicon is position 14. So it's actually easier to do than this one. Silicon is in group 4 in period 3. Now, group 4 is the second position in the P block for period 3. So this one goes 1s2, 2s2, 2p6, all the way across the second period into the third period. And when I get to the 3 Ps, I only need to count 2 positions in. If you've got a periodic table in front of you, stick your finger on it and count. Aluminum would be 3p1, silicon gets to be 3p2. All right, iron, off you go. This one's more difficult just because there's more numbers. And because the d orbitals were predicted by quantum numbers to appear in the third period, but they don't show up because the 4s jumps ahead of them, okay? So iron is 1s2, 2s2, 2p6, 3s2, 3p6. That's all the way out to argon. And then I get potassium and calcium, 4s2. And then I've got the D block, and I'm going to count scandium, titanium, vanadium, chromium, manganese, iron. So this is a D6. But remember, the 4s came out of sequence. This is not a 4d6, even though it's in the fourth period, it's the 3d6. Be aware of that. That might trip you up, okay? It's Friday already. Monday, we're going to pull electrons out and turn them into ions, or put electrons in and turn them into ions. Let's see what the configurations look like. That will be, I think, the last thing that we do in this chapter, and then we'll look at some shapes. Okay. There is a charity softball